Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. We were discussing the pipeline architecture with reference to computer architecture. We discussed last time our reference SRC, simple RISC computer, and added some additional hardware to make it a pipelined architecture. We just considered the example of having 5 stages, and we said that the latency is 5, and each stage requires the same amount of time, that is 1 clock cycle. Now we classified the set of instructions for SRC into 3 major classes, namely the ALU class of instructions, the load store class of instructions, and the branch instructions. For each class of instructions, we developed the required hardware interfacing each stage, and then finally we combined all these 3 classes together to have a complete hardware implementation for pipeline architecture of SRC. To control the activities of different stages and the hardware, we needed to have control signals. We defined the control signals in a combined fashion, like all the ALU functions were combined together to have one control signal. So instead of having individual control signals, we defined a set of control signals. Now, we stopped at this point and we continue today with the description of this pipelined implementation of SRC with the equivalent structural RTL description. And that we'll see in the following slide, how different stages are described using the structural RTL notation. This slide indicates the structural RTL description for the SRC pipeline. In the first stage, which is an instruction fetch stage, the contents indicated in the memory by PC are transferred to the instruction register. Now the instruction register written as IR2, as you remember from one of the previous lectures, 2 would indicate that this is an input to stage 2. So as a result of the instruction fetch, the memory location indicated by PC is fetched, and that is an instruction. You also remember that we have Harvard architecture. That means the memory for instructions is separate and the memory for data is separate. We have 2 portions of the memory, one for instructions and the other one for data. So as a result, we will have the contents of IR2, which are the contents obtained from the memory location PC. At the same time, the contents of PC are incremented by 4 and are stored into the buffer register PC2. Again, this is an interface between stage 1 and stage 2. In the second stage, the operation is decode and operand fetch. The first step, X3, indicates that the condition LS2 is checked. If this is true, meaning that if we have a load store instruction, only then what would happen? We check now further if RL2, which is true. That means if it is a relative addressing mode, then the contents of PC PC2 are transferred to X3. And then if displacement 2 is true, so if it was not a relative addressing mode, it was a displacement addressing mode, we check the value of RB. If it is 0, we place 0 into X3. And if RB is not 0, then the contents of register indicated by RB are transferred to X3. Again, this comma indicates that if it was not a load store instruction, rather it was BRL, branch and link instruction. Now 2 indicates the stage. I hope you remember we said that with each control signal, the numeral would indicate the stage which is in question. In this case, it is BRL2. That means that if it is a branch with link instruction and this is being processed by stage 2, then the contents of PC2 would be transferred to X3. And lastly, if it is an ALU instruction, the control signal defined by ALU2 would be true and the contents indicated by RB are transferred to X3. So as a result of this RTL description, we get the input to a multiplexer depending upon the type of instruction. If it is a load and store instruction, we get a relative address or a displacement address. If it is a branch and link instruction, we get contents of PC into X3, and finally contents of register RB if it is an ALU instruction. Similarly, Y3 would be analyzed in the same way. If it is a load store instruction, then RL2 would be true and we take the contents indicated by constant C1 into Y3. And if it is a displacement mode, then DISP2 would be true and C2 is taken into Y3. So all these different options are disjoint. So that would mean that we have either a load store instruction or a branch instruction or an ALU instruction. So for the case of branch 2, we do not do anything, nothing is required for Y3. And finally, if it is an ALU instruction, ALU2 would be true, and we move further, we check whether it is an immediate mode or not. So immediate 2 being true would give us the option of transferring the constant C2, of course, with sign extension into Y3 buffer register, or if it is not an immediate mode, we take the contents of register R indicated by RC into Y3. Now, if it is a store instruction, then store 2 would be true and we take the data indicated by register RA into the buffer register MD3. That means it would be passed on to the third stage with the buffer register MD3. Now the contents of instruction register IR2 are passed on to IR3. As explained in the earlier lecture, the instruction register contents are needed in every stage. So only the name would change and we will have IR2, IR3 and so on. So the contents of IR2 are passed on to IR3. The relevant contents would be opcode and RA. The others are actually, other bits do not matter. Finally, the stop 2 being true would place a 1-bit register run as 0. So in case that we need to stop the processor or this stage, we just put run to 0. The last action for this particular stage is to update the contents of PC. Now, if branch is not true, that means we did not have a branch instruction. PC would be incremented by 4 and it would contain PC plus 4. If the branch instruction is true, then we check the condition which depends on the contents of IR2, that means the constant part of instruction register 2 or the contents of register RC. So condition within brackets IR2, R with square brackets RC shows that condition would depend on IR2 and RC defined by these two values. So if this condition is true, the contents of register RB are placed into PC. That would mean PC would point to the next instruction to be executed. Finally, if the condition is false, that means not condition, in that case the PC would be incremented by 4 as done in the previous stage. Now the next stage is the ALU operation. In this case, the contents of Z4 would depend again on what type of instruction is in question. For load store instruction indicated by LS3, we add up the contents at the input X3 and Y3 to give the output of ALU indicating the address. If it is a branch instruction, branch and link BRL3, Z4 would contain X3. And if it is an ALU instruction, that means ALU3 is true, the operation indicated would be completed and we will have X3 op Y3. For example, if it was addition, then X3 and Y3 would be added. If it was an OR, X3 or Y3, and the result would be placed in buffer register Z4. The contents of MD3 are straight away passed on to MD4, and so is IR3 contents are moved on to the register IR4. The next fourth stage is the memory access. It needs to update the contents of Z5, which would depend on whether it is a load instruction or an ALU instruction. Now if load 4 is true, meaning that it is a load instruction, the contents of the memory pointed out by Z4 would be moved on to Z5. And if it is a load address instruction, LADR4 would be true, or if it is a branch instruction, branch 4 would be true, or if it is an ALU instruction, ALU4 would be true. In either of these three cases, the contents of Z4 are moved on to Z5. Now, if it is a store instruction, the data from MD4 is stored in a memory location indicated by Z4. So we will get, after the store operation, the memory updated by the data given in MD4 in a location indicated by Z4. And finally, IR4 contents are moved on to IR5. The last stage, which is a register write back stage, the register write 5 would be true and the contents available in the buffer register Z5 are placed into the register indicated by the placeholder value RA. Going through the previous slide, you might have a very clear idea of what different operations are done in different stages and what are the corresponding control signals activated at each stage. Now, we can just have a further strengthening of this concept of pipeline by considering a very simple sample program. We'll write a simple program and see how it propagates through the pipeline for our reference SRC processor. Let us see this example. In this slide, we have a sample code and we would like to see the propagation through the pipeline for SRC processor. The first instruction is arbitrarily stored at starting address 200. It's an add instruction, add R1, R2, R3. The next instruction is at address 204, which is a load instruction, load R5, within square brackets 4 plus R7, which indicates a register relative addressing mode. The following instruction is a branch instruction, branch R6 stored at address 208, and the last one at 212, which is a decimal address, store R4, 56. Let us see how these instructions move into the pipeline. The first instruction, which is an add instruction, enters the first stage, which is instruction fetch. And as a result, as add instruction enters the pipeline, the value in PC is incremented from 200 to 204, pointing to the next instruction. In terms of the hardware, you see at the first clock cycle what happens. The add instruction is indicated in the first stage. PC points to the instruction memory, which results the output stored in register IR2, and at the same time PC is incremented by 4 and PC is updated at the same time, and the contents also moved on to PC2. At the next clock cycle, the add instruction moves on to the second stage, the decode and operand read, and the next instruction, which is a load instruction, moves into the first stage, which is instruction fetch. So load instruction enters the pipeline. The value of PC is incremented again by 4 from 204 to 208. Add moves to the decode stage. Its operands are fetched from the register file and moved to the input of the multiplexer as X3 and Y3 at the end of the clock cycle. In terms of hardware, the second clock cycle is indicated. The first two stages are highlighted, and we have the multiplexers indicated. Output of the multiplexer with control signal MP3 gives us X3, one operand, and Y3 contains the output of multiplexer activated by MP4. The contents of IR2 are moved to register IR3. At the next clock cycle, the add instruction moves on to the third stage, which is ALU operation stage. The load from first stage moves to the second, and the third instruction, which is a branch instruction, enters the pipeline. The value of PC is incremented to 212 from 208. All these numbers are in decimal unless otherwise indicated. The third clock cycle in terms of hardware activates the first three stages. In the first stage we have branch instruction, in the second one we have the load instruction, and in the third stage ALU we have the add instruction. Finally, the fourth instruction moves into the instruction fetch, and the program counter is incremented to 216. It's a store instruction. The branch instruction has moved to second stage, and the third stage, the ALU instruction, the address is being calculated for load, and the results are written into Z4. In the case of memory access, add does not require any memory access. The result is therefore written to Z5 at the trailing edge of the clock. The fourth clock hardware operation is indicated in the next slide, which activates the first four stages. At the next clock cycle, the instruction fetches the next address, which arbitrarily is 400, that enters the pipeline. The value in PC is incremented from 400 to 404. The second stage contains store instruction, and it is in the decode stage the operands are being fetched from, for the case of address calculation, into X3 and Y3. In ALU, the branch instruction just propagates through this stage without any calculation, because no ALU operation is required. For the case of memory access, the load accesses data memory at the address specified by Z4, and result is stored in Z5 at the trailing edge of the clock. The register write back stage is writing into register R1 the result of the add instruction. As a result, the add instruction has been completed in the final stage. Again, the fifth clock cycle is indicated in terms of hardware. All the 5 stages are active. The first stage has got a new instruction, which is just arbitrarily, we don't know which instruction it is, at address 400. The other 3 instructions are in the pipeline: store, branch, load, and add has been completed and is out of the pipeline. The pipelined execution could also be shown in an alternate notation. Horizontally, we have indicated the 5 stages, and along the column we show the clock cycle 1, 2, 3, and 4. In the first clock cycle, the add instruction enters the first stage. In the next clock cycle, it moves on to the second stage, and the next instruction, load, enters the first stage. So if you go through the sequence, exactly the same information which was given in the previous figures is indicated in an alternate way, and movement of the instructions from one stage to the other are indicated. Now please note that the relevant stage just completes its own function and passes on the instruction in the trailing edge of the clock on to the next stage. For proper functioning of a pipeline, it is important that the dependency among different instructions is resolved. If it is not resolved, this would result in what is called the hazards. What could be different types of pipeline hazards? We could classify primarily these hazards into three categories. The first one would be the data hazards. As we explained earlier, that there is a dependence among different instructions. An instruction might require a data which is available after execution of an earlier instruction. So, by the time that instruction comes to a given stage and that data is not available, then there would be inconsistent data or a wrong data would be read into that instruction and the program would not be executed correctly. So therefore, this is important that the dependency is resolved. As we said earlier, either we could put delay loops or stall the pipeline, or we could forward data from one stage to the other so that there is no dependency or correct data is available. So therefore, this is what is called generally a data hazard. Now the second category of hazards is the branch hazard. Now whenever there is a branch, the PC needs to be updated and point to the instruction to be executed. Now if there is an incorrect data in the PC, the program counter, then the correct execution would not take place, and this could be an example of what is called a branch hazard. Now the third category of hazards is called the structural hazard. In the case of a structural hazard, the given hardware does not support that particular implementation, and there could be a situation when enough hardware is not available. For example, the multiplexer or other operands are available in such a way that the execution cannot take place. So that would be called a structural hazard. Now, in order to overcome these three different hazards, we'll just consider a couple of simple examples and illustrate the concept and see how these hazards could be eliminated. As indicated, a data hazard would occur when an instruction attempts to access some data value that has not yet been updated by the previous instructions. Let's take a very simple example of a read after write data hazard. We have two instructions. The first one is an add instruction. Add R2, R3, R4, which means that the contents of register R3 and R4 are added up and the result is stored in register R2. The next instruction is a subtract instruction, and it reads R7, R2 and R6. So the contents of register R2 and R6 are subtracted and result is to be stored in R7. The register R2 is written in clock cycle 5, and therefore the subtract instruction cannot proceed beyond stage 2 until the add leaves the pipeline. So therefore the subtract which needed the result placed in R2 as one of the operand has just availability of this operand in stage 2. So if it is not correctly available, then it cannot perform the subtraction correctly. So therefore this is an example of data hazard. The solution to such a data hazard could be that first detect. A data hazard can be detected as the operation and the operand are known before actual execution. The correction would depend, and it is dependent on instructions being delayed or stalled until the one ahead of them is complete. Or the second solution is data can be forwarded to the next instruction before the completion of the current instruction. Data forwarding can be done from the stage where it is available without waiting for completion of the instruction. The data normally required at stage 2, which is an operand fetch, is important, and data earliest available at stage 3 output, which is ALU result, or stage 4 output, which is a memory access result. Designing a data forwarding unit requires the study of the dependency distances, which means that what would be the minimum number of clock cycles required between the two instructions, and therefore the data could not be forwarded with a distance less than what is specified between the instructions. Now, this distance is indicated, the data dependence is indicated in the next slide, and different instructions, ALU load, load address, and branch with link are indicated, and the distances among the two for write and read from the register file are indicated. Now, one could note that without forwarding, the minimum spacing required between two data-dependent instructions to avoid the hazard is 4. So there is a minimum of 4 clock cycles required in order to avoid a data hazard for this particular example of SRC, taking into account the different categories of instructions. The load instruction has a minimum distance of 2 from all other instructions except the branch instruction. The branch delays cannot be removed even with forwarding and would require a minimum distance. The hazards could be detected by the compiler by analyzing the instruction sequences and dependencies. A compiler inserts bubbles, which is equivalent to a no-op instruction, between two instructions that form a hazard. The compiler solution to hazards is complex, expensive, and not very efficient as compared to the hardware solution. Let us next look at example of branch hazards. The instruction following a branch is always executed whether or not the branch is taken. This is called the branch delay slot. The compiler might issue a no-op instruction in the branch delay slot. Branch delays cannot be avoided by forwarding schemes. The branch hazard could be eliminated either by relocating the branch instruction itself, that means by appropriate rearrangement of the program, so it would depend on the skill of the programmer, or we could insert no-op instructions immediately following the branch instruction. In this way, we could avoid the branch hazard. Finally, the structural hazard occurs whenever there is a conflict as far as timing is concerned. Maybe the two instructions, they just try to fetch or utilize common resources, the same resources at the same time. And in that case, the structural hazard would occur. And as said earlier, using the Harvard architecture, that means a separate memory for instructions and a separate memory for data, usually avoids a major part of the structural hazards, meaning that at the time when data and the instructions are being fetched simultaneously, there would be no conflict because we have separate segments of memory for data and instructions. In other cases, if there is a situation of other hardware resources, this could be avoided by appropriate designing by the architect. Now, the resolution of these hazards, as said earlier, could be done either by hardware or by software. For the case of SRC, we could have a detection unit which detects the problem or a hazard, particularly the data hazard. And after that, it could resolve either by using a stall, that means inserting no op, or secondly by data forwarding. So as we said, it could be done by hardware. Doing it hardware-wise would be more efficient and faster. On the other hand, if a compiler writer has to detect and then finally correct the data hazards, naturally it would take more effort and it would be more time consuming and complex. Let us look at one example of the data hazard and its resolution in terms of the SRC hardware provided by the architect. Let us consider a typical SRC hazard correction through the pipeline stalls. Consider the following sequence of instructions going through the SRC pipeline. The first instruction is shift left R6, R3, 2. So there are two shift left by two locations. The next instruction is store R3 with immediate 32, followed by a subtract instruction, subtract R2, R4, R5, and followed by an add instruction R1, R2, R3, and finally with a load R7, 48. There is a data hazard between instruction 3 and 4. That means between the instruction subtract and add. And this could be resolved by using a pipeline stalls or the bubbles. That means by inserting the no op. Let us look at how it is done. As seen in one of the earlier slides, we just show horizontally the 5 stages of SRC, and vertically we show the clock cycles CC1 up to CC5. Now the first instruction is the shift left, and that has moved up to the last stage, and store instruction is in memory access, subtract is in ALU, add is in instruction decode, and the load is in instruction fetch, and that is what we consider as our first clock cycle 1. That means through the pipeline we have moved these 5 instructions. The first instruction is in the final stage and the last instruction is in the first stage. In the next stage, in the next clock CC2, the shift left instruction moves out of the pipeline and the store instruction moves from memory access to the register, and so the subtract is in memory access. And if we had an add instruction in ALU, the appropriate data would not be available in register R2. So therefore, we place a no op at third position at the third stage, meaning that we stall the add instruction into the second stage. We do not let it move to the next ALU stage. In the next clock cycle, we still insert another no op and push the subtract instruction from stage 4 to stage 5. So the store instruction moves out and subtract goes to the final stage. And therefore, we move in the fourth clock, the subtract instruction moves out of the pipeline, and now the data in register R2 would be available and could be used by the add instruction. So therefore, we see that a maximum of 3 no op instructions need to be inserted between the add and subtract. So this is the idea of what we call the stalling. So we stall and force the add instruction to remain in stage 2, which is instruction decode, for 3 additional clocks. It is interesting to see how could we write in the form of RTL a hazard detection and pipeline stall process. The slide shows the RTL description. The following RTL expression detects data hazard between stage 2 and 3 and then stalls stage 1 and 2 by inserting bubbles in stage 3. Now written in the form of RTL, it stands ALU3, which is a control signal indicating that the operation in stage 3 is an ALU operation, and ALU2, meaning in stage 2 we have also an ALU operation, and the third condition is RA3 is equal to RB2, indicating a common register between stage 2 and stage 3, or RA3 is equal to RC2. So both these conditions indicate a common register, a common operand, which is a destination register in one of the ALU instructions, and not immediate to. That means the instruction ALU instruction in stage 2 is not using an immediate operand. If this happens, this indicates a hazard, meaning that with 2 ALU instructions in stage 2 and 3 and with common registers and not immediate mode would indicate data hazard, and so therefore if it is true, it would be detected as data hazard. What needs to be done? After the colon, we see pause 2, pause 1, and commas indicate concurrent operations, and OP3 is loaded with 0, meaning that the op code 0 is a no op operation. So we pause the corresponding position, and 1 and 2 are paused with loading an op code of 0, which is actually no op. So we insert a no op instruction as a consequence of detection. So the first part of the RTL description detects the hazard. The second part installs the pipeline. So if op code in stage 2 and 3 are both ALU, and if RA in stage 3 is same as RB, or RC in stage 2 issues then a pause signal to insert a bubble between stage 3 and stage 2. Now the similar procedure for RTL hazard detection and pipeline stall could be written for other stages, and the table in the slide shows the stage 2 and 3, which has been repeated from the previous slide, and next two rows indicate the corresponding RTL description between stage 2 and 4 and stage 4 and 5. Let us interpret the data hazard indicated in the second line between stage 2 and stage 4, meaning that ALU4 and ALU2, which indicates that we have an ALU instruction in stage 2, also in stage 4, and RA4 is equal to RB2 or RA4 is equal to RC2 and not immediate 2. That means the ALU instruction in stage 2 does not use immediate mode of fetching the operand, and we have the common registers between stage 2 and stage 4 ALU instructions. Then pause 2 and pause 1 with opcode 3 is the solution to overcome and put the pipeline into a stall position. Exactly in the same way you could interpret the third line, which is between stage 4 and stage 5. We have today discussed how to introduce additional hardware to implement a pipeline architecture in our sample processor SRC. We have seen how to write the structural RTL implementation for different classes of instructions. We divided the total instructions into ALU type of instructions, store load instructions, and the branch instructions. Although we have seen that the throughput increases by using a pipeline, but it doesn't go without a cost. What is the cost? The hazards are there, and for proper designing we need to detect these hazards and also then remove these hazards. So we have discussed one way of doing that, and that was whenever a data hazard is detected by the implementation or by the hardware implementation, we just introduce no ops in between the dependent instructions. We discussed one example where both the instructions were ALU instructions and one required as an output fed to the other instruction. So therefore we solved this problem by stalling and maintaining a particular instruction in stage 2, moving the other instruction out of the pipeline, and in between we introduced no op operation, or we have written an RTL description for this particular detection and the stall process, or how to stall the pipeline. We are going to go into more detail of the second solution for overcoming the data hazards, and that is the data forwarding. We'll discuss that in more detail next time as far as the technique of data forwarding is concerned. This is an appropriate point where we can stop for today, and we'll continue with the further concepts of removing the data hazards by using the data forwarding techniques. So next time we'll be further discussing the data hazards and the solutions to it, and for today that's all. Till next time, Allah Hafiz.